Have you ever stopped to think about how completely different things in our daily lives are actually driven by the exact same invisible physics? I mean, think about it. How do the exact same fundamental laws power the cell phone in your pocket, the sound of your own voice, and that laser pointer you use in class? It sounds like magic, right? But it really all comes down to one absolutely elegant concept: waves.
Welcome to This Explainer. Today, we're going on a really fun journey to demystify the hidden rules behind both light and sound. We're going to strip away the super complex equations and look at how engineers actually use basic physics to build our modern world. If you're studying physics, these are some core concepts you'll definitely want to master.
All right, so here's our roadmap for today. First, we'll look at the fundamental nature of waves. Then, we'll see how they bend, bounce, and refract. After that, we'll explore how technology guides those waves, switch gears to acoustic waves, and finally, wrap up with the physics of lasers. Let's get right into it.
Section 1, the nature of waves and understanding the disturbance. Let's dive right in by defining what a wave fundamentally is. And if you're taking an exam on this, you absolutely need to nail this definition. A wave is basically a periodic disturbance that propagates through a medium, or with light through the vacuum of space itself. Crucially, it's a way of transferring energy from one place to another without transferring matter overall. The wave carries the energy, but the particles themselves do not travel with the wave. This breakdown brilliantly illustrates the core differences between our two main wave types. Over on the left, we've got electromagnetic, or EM waves. These are transverse. That means the electric and magnetic fields vibrate at right angles to the direction the wave is actually traveling, kind of like ripples on a pond. Then, on the right, we have acoustic waves. These are longitudinal. The vibrations happen in the exact same direction the wave travels, creating this series of physical compressions and stretches in pressure.
Now, what's really fascinating here is the mathematical consistency. Look at this visualization. Whether it's a massive antenna radiating energy across a city or just a voice echoing in a room, the wave spreads outward uniformly. The core math stays exactly the same. Only the physical variables change. It's really just energy moving outward from a source.
Moving right along to Section 2, bending, bouncing, and refracting. Because we have to ask, what happens when these waves hit a boundary? Well, they don't just stop, they interact. And that brings us to the absolutely crucial concepts of reflection and refraction.
So let's talk about Snell's law. This is the physical principle that mathematically governs how waves bend. When a wave passes from one medium to another, say from air into glass, its velocity changes based on the material's refractive index. That's basically a measure of how optically dense the material is. Because the speed changes, the wave's path literally bends. This one single concept explains classical phenomena ranging from why the sky is blue to the exact curvature you need to make a magnifying glass work.
But here is where it gets totally wild. If the wave approaches a boundary at a shallow enough trajectory, we hit something called the critical angle. At this specific angle, the wave doesn't bend or refract through the material at all. Instead, it bounces back entirely into its original medium. We call this total internal reflection. And let me tell you, this phenomenon is the absolute backbone of modern global communications.
Which leads us perfectly into Section 3, guiding waves through tech. This is where we start trapping light and energy. You see, engineers realized they didn't just have to let waves radiate randomly out into space. By harnessing that exact total internal reflection we just talked about, they could actually trap waves and build some truly revolutionary technologies.
Take a look at this representation of an optical fiber. By designing a glass core that has a higher refractive index than its outer layer, light gets continuously trapped by that critical angle. It hits the edge, total internal reflection kicks in, and it bounces perfectly down the line. This is a huge deal. It allows us to transmit vast amounts of internet data globally across oceans with almost zero loss. It's essentially a perfectly engineered light track.
And we use a really similar concept with metallic waveguides too. By creating highly precise boundary conditions, essentially forcing the electric field to be zero at the perfectly conducting metal walls, specific standing waves stay perfectly confined inside. So, whether it's the waveguide inside your microwave oven heating up your leftover pizza, or the feeds powering giant cell phone antennas, we're literally just forcing EM waves to adapt to mathematical boundaries.
All right, Section 4, acoustic waves and resonators. Let's switch gears and talk about the physics of sound. Like we established earlier, acoustic waves operate on similar mathematical structures to EM waves, but they fundamentally require physical matter to exist and travel, things like gas, liquid, or solids. If there's no medium, there's absolutely no sound.
Because sound relies on physical molecules literally bumping into each other, Its speed scales up dramatically as the medium gets denser. Check out this table. In freezing air, sound travels at about 330 meters per second. But put it in water, and it jumps to 1,500 meters per second. And in rigid solid metals, where the molecules are packed super tightly, it can exceed 13,000 meters per second. The medium physically dictates the ultimate speed limit.
So how does this apply to you? Well, the human vocal tract is actually a natural acoustic resonator. Depending on its shape, it naturally amplifies specific frequencies. And you know what? This perfectly explains the famous bathroom opera effect. When you're singing in the shower, the specific dimensions of the room act like a giant resonator. Your mouth acts as a velocity source, and your voice hits the acoustic sweet spot of the room, perfectly matching the boundaries so the sound waves bounce and stack up. Suddenly, physics makes you sound like a professional opera singer.
Finally, Section 5, the physics of lasers, harnessing the quantum. We're graduating from everyday macroscopic physics to actual quantum manipulation. We're going to look at the ultimate directed electromagnetic wave, the laser.
The physics of lasers requires us to do something pretty unnatural. Normal physics dictates that atoms want to rest at their lowest possible energy state. But to make a laser, we have to create what's called a population inversion. We basically force a massive amount of atoms into an excited high-energy state all at the same time. When we successfully manipulate that quantum state, it gives us a highly structured, coherent beam of waves. We can break this amazing amplification process down into 4 distinct steps. First, an energy pump mechanism repopulates the upper energy level, forcing the atoms up. Second, one atom naturally drops down, releasing a single photon in a spontaneous emission. Third, and this is the real magic, that photon strikes another excited atom, triggering a stimulated emission. It forces that second atom to release a photon that is perfectly identical and coherent with the first one. Finally, we put mirrors on both ends. These identical photons bounce back and forth, creating an exponential chain reaction until a powerful, directed beam bursts through.
So, what should you really take away from this explainer today? It's the incredible unity of the physical world. Whether it's an acoustic wave compressing the air to carry your voice, an optical wave trapped perfectly inside a glass fiber to load a web page, or a coherent laser utilizing quantum states to slice through solid metal, they are all governed by the exact same elegant mathematics. It's all just a periodic disturbance interacting with its environment.
We've literally built the modern era simply by understanding how to bend, bounce, trap, and amplify these waves. So I'll leave you with this final provocative thought. If we can perfectly master light and sound using these ancient equations, manipulating everything from physical air pressure to quantum states, what invisible forces will we engineer next? Keep that in mind the next time you connect to Wi-Fi or speak into a microphone. Thanks for joining me on this explainer, and keep questioning the world around you.